Can you hear me in the back? Great, thank you. Friday is a special topics lecture by the TAs, by the way, if you haven't seen that. Should be really fun, but it is optional. So, if you're like too busy working on the homework or something like that, it's not stuff that's examinable. It might just be stuff that you might be interested in. Yes? What is it on? You'll get a more accurate answer if you ask on Piazza, but I think there's a couple of different topics being floated around. Maybe it'll be some mix of these things. There's like variational inference and variational autoencoders, which I very briefly alluded to, but I didn't actually tell you what they were. And then maybe something like bandit algorithms for reinforcement learning and things like that. So, in general, in the same space as what we've been doing, but not core topics to the class, just something that you might be interested in seeing and learning more about. So that's Friday. Today we're wrapping up ConvNets. All right, so what did we do last time? Last time we talked about, what ConvNets look like in terms of their structure. It wouldn't be terrible to just stop there, because, typically the way that people use ConvNets is they'll use some like library that makes deep learning a little bit easier, like PyTorch or TensorFlow or one of these things. And then if you use something like that, all you have to do is really define the structure of the ConvNet, what we did last time, right? You don't really need to do things like compute the gradients by hand or all this other type of stuff. That kind of stuff is done for you, right? So if we were, just interested in that, then that'd be good enough. I do want to show you a little bit about what this operation that ConvNets is performing actually looks like in math and work out its gradient, not because you're necessarily going to need it one day, just because I think it's cool. And it might give you a little bit more insight into what this convolution is actually doing, or what this conv layer actually ends up doing. So on homework 5, you'll be working with like fully connected networks, actually programming them in terms of not only their structure, but how you actually compute gradients and all that other kind of stuff. When we go to ConvNets in homework 6, you'll no longer need to worry about that gradient computation. So you'll at least be saved there, although you will have to learn things like how PyTorch works and stuff like that. So this lecture is not going to be on the homework, but hopefully it's still interesting because it sheds a little bit more light into what it is that we're actually working with. Yes? I believe ConvNets are on homework 6, yes. What homework are we on right now? 5, right? 5, because we started from 0, right? That's the PyTorch tutorial in this homework, right? So I think next homework is when you'll actually be building and training the ConvNets, but I could be mixing these things up. Got it. Okay, well, so homework 5 then. Maybe homework 6 too. I actually don't even know how these things are split up. Nevertheless, you'll never have to do this gradient computation in a homework by hand. So you can relax if nothing about this lecture makes sense. It's merely there because I think it's interesting to show you, and hopefully it'll shed some light onto these things. Something else that we haven't done a whole lot of in this class is talk about recent history in machine learning. Why is that? It's because most of recent history, at least in the research community, has been around deep learning. And we haven't really started talking about deep learning until, the last couple of weeks. So one thing that I'm going to do this week and next week is tell you a little bit about, what machine learning research has looked like in the last 10 years. Of course, you're not going to get the full detail of, all these different papers and things like that. But we'll have, citations if you want to go look up the paper yourselves. And it's good to know a little bit about, sort of what the advancements have been and what it is that we're capable of doing and, where we might think about going in the future. And then next week, we'll round out our deep learning discussion by covering another type of neural network called the transformer, which has become, extremely popular over the course of the last 5 years or so. But that's sort of the roadmap for the, most of what we're doing in the rest of this course. But first, we do math. What do convolutions look like in math? Let's start with the forward direction. So, actually processing an input using a convolution into the output. Okay, let's call our input AL because it's like the output of the previous convolution layer. Okay, so like something that's already gone through the conv, batch norm, ReLU kind of thing, and then we're given an AL, and it's got, it's image-like, right? So it's got some height and some width and then some number of channels, right? Some depth is what we call it. And we're going to process this using a convolution operation into ZL plus 1, which is the thing that's going to go into the next like batch norm ReLU kind of thing, right? And this is going to have some other height and some other width depending on these hyperparameters that we have, right? Like the padding and the stride and all that other stuff. And then also some number of output channels, C prime. So the filter that we're working with in this convolution, we're going to call this WL plus 1. So it's just our weight tensor, right? We used to say weight matrix. Now these things are kind of higher dimensional. Let's call it a weight tensor. It's got height and width size K by K, right? And then it's outputting C prime number of channels, and it's taking as input C number of channels, right? So each one of these C primes, right, what it's doing is we're doing a complete element-wise multiplication, right, of that K by K patch in the input, right, which has C different channels, and then we're summing all those numbers together, and that's how we get one of our outputs, and then we get C prime of those. And then we slide this across our whole image in order to get H prime, W prime, and C prime as the output shape. What does that actually look like? Well, let's work it out. So if we have Z L plus 1, and I want to know what's the, I, J, kth element of Z L plus 1. Well, what's that going to be? It's going to be my filter, WL plus 1, right? Element-wise multiplied by all of the respective parts in AL that I actually care about, right? So what do I care about? Well, here, I and J are sort of like the height and width that particular quote-unquote pixel that I'm looking at in ZL plus 1. What determines that? It's that corresponding patch in my input AL, right? So that patch is going to be, starting from, I and J, and then moving across, by, whatever the filter size is, right? By like K this way and then K that way. So this ends up looking like this particular sum. I can write it, right, as a sum from, let's call the first thing 0, and this goes from 0 to K minus 1, right? This is like sliding across the width of the input, or this is like going across the width of the input, right? Second thing is B, this is going across the height of the input. And the last thing is summing across all of the different input channels that I have. I have C of those, right? So not C prime, C. Like C is the number of channels that I have in my input. And what am I summing? Well, I'm summing, this corresponding weight that I have in my filter. So this is going to be A, B, right? That's like my height and my width. What's the third index? If I specified that my filter has shape, K by K times by number of output channels by number of input channels, what's the third index that I should be supplying for this W? Yes. 1. Well, it's not necessarily the first output channel that I'm outputting, right? Which output channel am I looking at? K, right? Little k, right? So it's little k, right? That's like the ZL plus 1 last index, right? And then the last thing is this C that I'm summing over. And what am I looking at in my input? In my input, right, I'm looking at, I'm looking at this patch where the top left is the ijth, pixel that I have in my input. And then the patch that I'm looking at is, big K wide and big K down, right? So basically, I'm looking at something that looks like it starts from I, but I'm adding A. I'm running out of room here. And then the height starts at j, but I'm adding b. And that's how I'm considering all the different parts of the input that are part of this patch that I care about, right? And the cth channel. Ran out of room there at the end, but you know, all of that should be on the same line. So this is basically what my convolution looks like in the forward direction. I just compute ZL plus 1 for all of these ijk, right? I ranges from 0 to h prime minus 1, j ranges from 0 to w prime minus 1, and then k ranges from 0 to c prime minus 1. We're zero indexing everything, right? But this is basically how we're going to compute our output ZL plus 1. Naively, I could do this as a triple for loop, right? One for loop for each of ijk. What I can actually do is make it a little bit more efficient by doing some like matrix computations rather than for loops and being a little bit smarter. So one way that we can sort of see one of those ideas is I can write this instead in matrix vector notation, our favorite, right? And we can say that ZL plus 1, just ij now. What is this? This is a C prime dimensional vector. Okay? This is equal to just a double sum where I do over A and over B, but I can leave out this last summation over channels because I'm just going to do basically a matrix vector product between the corresponding part of my W with that corresponding part of my A. So then this ends up looking like W L plus 1 of AB. What is this? This is a C prime by C matrix, right? And then AL I plus A, J plus B. What is that thing? What is AL of I plus A, J plus B? Yes. It's a C-dimensional vector. Right, so this makes sense, right? If I multiply a C prime by C matrix with a C-dimensional vector, I get a C prime dimensional vector out, which is what I want. And then I'm summing together all of those vectors that I'm computing, element-wise. Right? And then that gets me on my C prime dimensional vector. Yes? So why are we doing I plus A and J plus B? This is a great question, right? So remember what the convolution is doing, right? So this filter is sliding across my whole image, and then at any particular point, right, of where I'm at in my image, that's what's going to produce that output in ZL plus 1, right? So we can ask the question, what produced ZL plus 1 at the ijth position? What was that? Well, it was based on this patch in my input that's sort of what we can say like anchored at ij, that's like the top left, but then we also span k this way, big K this way, and then big K down as well, right? Right, so we're not considering the middle point because that makes the indexing way more tricky. It's a little easier to just say that like the top left is ij, and then I'm just adding A and B for values of A and B between 0 and K minus 1. It would be the same thing. It would just look a lot less pretty than this, which already doesn't look that pretty. Yes? Great question. Does this consider stride? No, it does not. So this here is stride of 1, right? And if we wanted to have a larger stride, we would need to basically multiply that stride into I and J, right? So that, or for like the AL in the input, right? So that we're moving over in larger chunks for our AL. That, again, makes things more complicated. We left that out. There's no padding in here, right? And I didn't specify what we're doing for that. Although that one's a little easier. We don't have to change anything about the equations. We would just have to change like the specification of like how large AL is, right? But we're leaving out all those things because it makes things significantly more complicated. And stride of 1 is way more common anyway. Yes? Yeah, what is this little k in the WL+1 indexing? It's this k out here. Okay, so I'm looking at, well, basically I want to compute the full ZL+1, which is going to be h prime by w prime by c prime, right? Here, the equation is being written out in such a way that we're only considering how do I compute the ijk element of ZL+1, and then we can write like a triple for loop to compute all the elements of ZL+1, right? But the ijkth element of ZL+1 in particular is computed using only the corresponding like output channel in this WL+1, right? So this WL+1, this C prime here corresponds to this C prime over here, right? And so this K is indexing into the particular dimension of output channel that I'm actually considering when I'm considering the Kth thing of ZL+1. Does that kind of make sense? Ask all your questions now, because it only gets more confusing from here. Yes? Sorry, I think I missed part of the question. So the triple sum... There's an edge from every... You mean from every input dimension to every output dimension? So there's not, right? Because, you know, for example, intuitively, right, like AL in like the bottom right, does... In the K by K little box or patch that we're looking at, yeah, there's an edge from every part of every patch of AL in there to like that output. Yeah. But like there's no like very like long-term dependencies or anything like that. So yeah, significantly less connected than like a fully connected network. Okay. Sear this into your mind. This is what the forward direction of a convolution looks like. It's kind of this triple sum, or it's like a double sum if you want to write it as like, you know, a matrix vector product of like, you know, some filter multiplied element-wise by some input, right? That's what it is that we're going for, right? Yes? Yeah, so padding doesn't actually change this equation. That's correct. It just changes how large the ZL+1 is at the end. If you're mathematically inclined, you might be saying, this is not a convolution. I didn't flip my filter. That's okay. We don't worry about those things. I mean, the parameters in the filter are learned anyway. So flipping it wouldn't really make a whole lot of a difference. It's a little easier to just write things out this way and implement them this way as well. Anyway, triple sum or double sum of a filter element-wise multiplied by my input. That's what convolution the forward direction looks like. What does convolution the backward direction look like? We're not going to work this out in extreme excruciating detail because that's no fun. We'll do something that's slightly more fun, which is work out a simple case where we assume that input channels equals number of output channels, which is 1. Okay, so we can sort of drop that last sum that we had. Okay, that's going to make things a little bit easier. So here, when I write out this thing that looks a whole lot like this matrix vector product that we had before, right? This is actually now just scalar-scalar products, right? Because there is no C and C prime anymore. Those are just fixed to 0 because you know, each one of those, there's only one channel in the input and the output. So when I write out something like this, this actually means, you know, just multiplying numbers together and then adding them up. How would I compute the loss with respect to, you know, the things that I care about? What do I care about? I care about computing the loss with respect to my filter, right? Because those contain the weights that I'm trying to update, right, to make them better. I also care about computing the loss with respect to my input, AL, right? Because that's what I'm going to back propagate in order to compute the gradient with respect to the parameters at the layer before me, right? WL. I also need to compute the gradients there. So there's two different gradients that I'm interested in. Let's try to look at the gradient with respect to the input AL first, because that's going to look a little bit simpler. So we're looking at, let's actually compute this local piece first. So we have ZL plus 1. What is the partial derivative with respect to ZL plus 1 at the ijth index with respect to AL at the I plus A index, J plus B index? Can anyone tell me what this partial derivative is? Don't overthink it. Yes. Yeah, I mean, it's right here on the page, right? It's just WL plus 1 AB, right? So the partial derivative with respect to this particular piece of my output, right, with respect to this particular piece of my input, right, this is just one partial derivative, right, is just the corresponding A-B entry in my filter. Remember, here we're leaving out all the C's, right, because we're assuming that we only have one input, one output channel. There's an analogous story that you can tell there. It just looks a little bit less pretty. This equation holds for all A in 0 to k minus 1, and for all B in 0 to k minus 1. Okay, so for a fixed ij, right, so for a fixed point in my output, its partial derivative with respect to that patch in my input is given by this equation, which indexes different ABs in my filter. Okay, does that part make sense? So let's say now I wanted to compute the actual gradient or the derivative of the loss with respect to one particular point in my input. Remember, why do I want to do this? I want to do this so that I can back propagate it into the previous layer so that I can compute gradients with respect to that filter as well, right? That's the goal, right? So this is why I'm doing this. To make it a little bit simpler, let's just consider computing the loss. So now I'm almost doing like a change of coordinates, so to speak, right? I'm using the same letters, but it's a little bit of a change of coordinates. What's the derivative of the loss with respect to the ijth input AL ij? Well, what I need to do in order to compute this, right, is to consider basically the law of total derivatives, right, where I have to like add together all of the different partial derivatives that I'm getting. What partial derivatives am I getting? Well, it's whatever AL touches in the output, so to speak, right? Remember, we have these local connections, right? Which means that AL does not influence every single part of ZL plus 1, right? AL only comes into play for a small piece of ZL plus 1. It's whatever is included in that. It's whenever it's included in that patch that we're looking at, right? When is AL ij included in the patch? Well, it's included whenever ZL plus 1 is within this window of I minus up to k minus 1, right? And j minus up to k minus 1. Remember, this is like a change of coordinates, so I'm actually moving backwards, right, rather than moving forwards, because now I'm going from z to a rather than from a to z. So I have some number of ZL plus 1 that are actually influenced by AL, right? And I can index all of those, right, as like I minus A and J minus B for 0 to K minus 1 for both A and B. So I have the loss with respect to all of those things. That's what I get when I back propagate, right? And now I've also computed this gradient with respect to any dimension of Z and any dimension of A. So I just need to put those two together using the chain rule, and then add all of those together to get my final derivative, because it's just going to be the sum of all those derivatives put together. So in math, here's what I'm saying. We have a sum of over a and b. And we're going to write this in a similar way like what we had before. A and b both go over this k minus 0 to k minus 1 window that we have. And then what we have is the derivative of the loss with respect to what are all of the ZL plus 1s that get influenced by AL, right? Like ALIJ is part of the computations for which ZL plus 1. It's all of these I minus A, J minus B pieces of ZL plus 1. So all of those dimensions are what get influenced by ALIJ. And what's the derivative of ZL plus 1, I minus A, J minus B, with respect to ALIJ? Well, if we look at this formula up here, right, I've basically done a change of coordinates, but nothing else particularly interesting, right? I'm just looking at the difference between those coordinates, right, of I minus A, J minus B versus IJ. I could just as easily say IJ and I plus A, J plus B, and those kind of mean the same thing, right? So here, the derivative is going to be WL plus 1 AB, just like what we had before. So this becomes the derivative of my loss with respect to one dimension of my input, ALIJ. And I can compute this for all I and all J. And if I had an extra channel dimension, an extra depth, I could also compute it for all of that, right? Which sort of gives me the full gradient with respect to my input AL. Yes? I'm sorry, you're going to have to point out which part. Oh, no. I did the thing again. Well, that's unfortunate. Well, I'm going to write this last part that we had, okay, which is DL, and I'll write it out in a little bit more detail, which I think is going to answer your question, but let me know if it doesn't. Is this sum of WL plus 1 AB, I'm switching around the terms for no good reason. Oops. Does that answer your question? Perfect. Does this look like anything? I know that's a really vague question, but I'm happy to wait to see if anyone can stare at this hard enough that they can tell me that it kind of looks like something. Yes? It does look like a neural network, sort of. The gradients with respect to, oh yeah, the gradients that we had, I mean, yes, so it definitely looks like what we had before with backpropagation, with taking into account sort of the special structure that we have in the neural network. That is definitely true. Think more recent, like, you know, last 30 minutes kind of recent. Yes. It kind of looks like a convolution, right? So the backward pass that we're implementing here, when I compute a gradient with respect to AL, it actually kind of looks like a convolution, right? It's a convolution between the same filter that I had, WL plus 1, just with a different input. The input used to be like AL was the input. I would convolve that with WL plus 1 to get ZL plus 1. Now it's like the gradient with respect to AL is the output, and I'm convolving my filter with the gradient that I got from my backward pass, right? The gradient with respect to the output ZL plus 1, convolve that with WL plus 1, then I get my next gradient. This is kind of interesting. Why is it kind of interesting? It means that I can just basically have one function that computes convolutions, and then that function can be used both forward from ZL to AL, from AL to ZL plus 1, and backward from gradient of ZL plus 1 back to gradient of AL. Okay, so that's kind of the big idea, and that convolution in these cases is actually using the same filter to convolve. It's just this WL plus 1. Okay, so this WL plus 1 actually ends up getting used in two ways. It's to do the forward pass, and then also to do this backward pass to compute the gradient with respect to the input AL. You'll notice here that the convolution used to be like I plus A, J plus B, things like that. So technically you have to like flip your W to get the right thing, but it's still a convolution in the end. You just kind of have to like, transpose what it is that you're actually looking at. Yes. Does that save you computation? Not really. But if you have like an efficient implementation of a convolution, then you can use it in both forward and backward and sort of save, the time that it would take to sort of, write these manually, and also, it'll be efficient both forwards and backwards. All right, doesn't seem so bad so far. Let's make it worse. So we're not done yet, right? Because we've computed this gradient with respect to my input AL. I need that for the backpropagation, but that's not actually the goal. The goal is to compute the gradients with respect to all the weights, all the parameters, which in this case is my WL plus 1, my filter. Because I need those gradients in order to know how do I update my filter, change those parameters in such a way that I'm going to get lower loss. That's the idea that we're looking for here, right? So we need to compute the gradient of the loss with respect to WL plus 1. So let's do that. Well, let's actually first compute sort of this local piece again, right? What is d ZL plus 1 ij d WL plus 1, AB? These two kind of use different coordinate systems, right? Like I and j go from, 0 to h and 0 to w, and a and b go from, 0 to k minus 1 each, right? Well, this derivative of this particular piece of my output with respect to this particular weight in my filter, if I just look at this equation up here, I can see that it's just AL I plus A, J plus B. That's all I need, right? That's like the only piece that I need to, extract from the sum that we've written here, and because it's just a multiplication, I know that it's just going to be that corresponding entry in that multiplication. AL, I plus A, J plus B. So then from here, we can try to ask the question, well, what's the overall gradient or derivative with respect to the loss of WL plus 1 AB? I ask you a slightly tricky question. So before, right, when we were computing this with respect to AL, the input, we were looking for all of the pieces of the output, all of the dimensions of the output that actually depend on that particular dimension of the input. Which dimensions of the output depend on WL plus 1 AB? Yes. Right, so what we're looking for is what dimensions of the output, ZL plus 1, depend on a particular entry in my weight matrix. Okay, so that's the question that we have. Yes. All of them, right? So we no longer have this nice, like, locally connected structure or something like that. Actually, we have to consider all of the dimensions of the output because they're all influenced by any particular dimension of my weight matrix. That's just how it does, right? I slide my weights across my input, but the whole weight matrix influences how I get my output, right? For any particular dimension of my output. So here, what I'm going to need is, again, two sums. I'll call them I and j because that's what we called them before, but they have to go across the entire output from 0 to h prime minus 1 and 0 to w prime minus 1. Okay, so there's no like nice small k or anything like that we can look over. We have to look over the whole thing. And then this becomes the gradient of the loss with respect to that particular piece of my input, right, ij. And remember, this is what we're assuming we're getting from backpropagation, right? Backpropagation is giving us the gradient with respect to ZL plus 1. We're using that, using the chain rule, in order to compute the gradients with respect to WL plus 1 and AL, like we did on the previous slide, right? And if I combine this with a chain rule, I need DZL plus 1 IJ and DWL plus 1 AB. This is just what I've already found, which is just AL I plus A, J plus B. This, too, is a form of convolution. What's my filter in this case? If I interpret this as a convolution, what's my filter? Yes. It's AL, right? So now my filter is no longer WL plus 1, it's AL. And I'm convolving that with respect to DL, DZL plus 1, right? The same thing that I had before. So basically, when I do my backward pass in the convolution, I convolve two different filters over this gradient that I'm getting. And then one of the filters is the actual filter that I have, WL plus 1. The other filter is this input, AL. And I use those to get my gradients with respect to the input, AL, and the filter, WL plus 1, respectively. Yes. So I'm not sure if I fully understand the question, but like the filter that we have here, right, like A and B are fixed, and we're like considering, given that A and B, like the entire like 0 to h prime minus 1 and 0 to w prime minus 1 of that part of the input, right? So it's like a very large piece of the input AL. But it's not the entire thing, yes. It's going to be different, right, for the different A's and B's in the WL plus 1. Yes. Why are we not considering a bias term? It's too lazy to write out the math. But that one's significantly easier. You can figure that one out on your own. Doesn't look that different from the bias term that we had previously. I just wanted to show you this part because it's basically just 3 convolutions. You implement convolution once, you can use it for your forward pass, AL to ZL plus 1. You can use it for both of your backward passes, right? Gradient with respect to ZL plus 1 and gradient with respect to all the things that you need, WL plus 1 and AL. All of these things are convolutions. You just pass in different filters when you're trying to, and different inputs when you're trying to compute all these different pieces. And that's pretty much it. So again, you will never have to implement this, but I think it's cool. I think that's enough math for one day. Let's do something easier. Just talk about what the last 10-ish years look like in ConvNets. This number 10, it's chosen very carefully because there's this big thing that happened in 2012, which kind of, spawned, most people agree that this is sort of what spawned the whole deep learning revolution of the last decade. And it's this model called AlexNet. So AlexNet is a convolutional network, right? So these ConvNets we can sort of think of as basically driving, at least, for the first part of the decade, all of that hype in terms of, why deep learning was so popular. This model came out in 2012, and it came out in, in one of these conferences that we have. And it really I already said this. It really started the past decade of deep learning hype. This is really what drove it. Because what it did was it really first comprehensively demonstrated this power of combining very expressive models, with like, it's very, very large convnets with like millions of parameters. Millions is small now, right? But back then it was pretty big. With lots of compute. So, like 2 big beefy GPUs and training for like a bunch of days, which back then was also a lot of compute. Nowadays it's kind of small, but that's just how things progress. And also a ton of data, right? So basically what they applied this thing to was something called the ImageNet Large-Scale Visual Recognition Challenge, ILSVRC, or people just mostly call it ImageNet. So ImageNet, basically this challenge means something slightly different than when people just say ImageNet, but the basic idea is you get tons of data, and then you train whatever model it is that you want, and then you report the performance, and it's like a very, very difficult task because there's so much data and so many classes and things like this. And performance had really kind of plateaued until 2012 when someone came out with AlexNet and showed that you can sort of blow all these other approaches out of the water using this. And this is what really started that hype train for why deep learning is so talked about today. So what is ImageNet? The images in ImageNet are 224 by 224 by 3. That's why I keep telling you those numbers. And they evenly cover 1,000 different classes. Okay, so it's a 1,000-way classification problem. You can imagine this is quite a bit more difficult than things like digit recognition, like 10-way classification. As you scale up the number of classes you have, your problem really becomes, in some sense, exponentially harder. So 1,000 classes is quite a difficult problem. And a lot of these classes are very closely related to each other, right? So you have like many, many different subbreeds of dogs and things like this, and you have to be able to distinguish, do fine-grained classification to distinguish between all of those different breeds. That sounds like a difficult task, but what we're able to do is use a ton of data to try to learn this task. So there's over 1 million images that we use for training, right? So this is quite a bit larger than a lot of the data sets that we play around with for other domains, but this is really quite standard for deep learning at this point. And then we can use a separate 50,000 images for evaluation. This is actually the validation set. But people use this validation set to report performance because we don't have access to the test set. Because the test set is actually what goes into that challenge, the ILSVRC, that we told you about on the previous slide. So they never release the test set. You can submit and to the various challenges every year and see how you do on that test set. But if you want to report performance for like a research paper or something like that, then the validation set's kind of the best thing that you got. It doesn't just stop there. Now we play around with even larger versions of ImageNet, like ImageNet 22K, which is basically about 10 times larger. There's like 10 million training images, something like this, and 22,000 classes. So now we're doing 22,000-way image classification, which, if you had told this to somebody like 10, 15 years ago, they would have thought it's completely unfathomable. But this is basically what deep learning buys you. As you make your models bigger and you increase the amount of compute you're willing to use, the hardware gets better and you're willing to wait around for longer and stuff like that, and you increase the amount of data. So like, make your data set 10 times larger. You just keep expanding the potential of what your models are able to learn. And this type of scaling is not really something that you see for basically any of these other models that we've talked about in this class. Not that those models aren't useful, right? They're useful for a lot of different problems, but if you want scaling, if that's your main goal, then it seems like deep networks are sort of what's going to buy you that in by far and away, the most, convincing way. Nowadays, for computer vision applications, in particular, it's very common to start not from scratch, so I don't initialize my parameters from scratch. I instead download some pre-trained neural network, usually like a ConvNet or something like that, off the internet, okay? So people will, post the models that they train with their various methods and things like this, on GitHub or something like that. You just download one of those, and that's where you start from. Rather than starting from scratch, it makes learning on what we call downstream tasks, like some new image classification problem, usually work a whole lot better. And we don't require as much data for the new task because this network has already seen so much data on ImageNet. So oftentimes this is sort of where people start from in order to sort of maximize their performance that they might be able to expect. Yes? Yeah, so when I say downloading, basically what I mean is like, download some set of PyTorch weights from some repository on GitHub or something like that, and then load those in, and that becomes the network that you start from. Yeah. Oftentimes works a whole lot better than trying to initialize your weights randomly. ImageNet's not the only thing. I mean, it's not really great for prototyping because it's so large and you have to wait around for a while. So there are these smaller image classification data sets, right, that we also play around with. Is MNIST a part of homework 5? Okay, it might be a part of homework 6 then. CFAR is part of homework 5? Wow, we're getting ambitious out here. All right, so MNIST, CFAR 10, CFAR 100. These are better for prototyping, and ImageNet is not because it's got a million images, and they're kind of large, and the problem's kind of hard. So you can't really quickly iterate on this when you're trying to, play around with your model, right? Like pick various hyperparameters or do a little bit of research or things like this. These three data sets are much smaller, and they sort of increase in difficulty in the order that they've been listed in. But they're all much easier than ImageNet. Over here is a picture of CFAR 10. There's 10 different classes. So MNIST only has 60,000 images, which is 2 orders of magnitude smaller than ImageNet. And it's only got 10 classes, which makes the problem significantly easier. And it's got these much smaller grayscale images that we work with, right? And this is a digit recognition problem. They're like trying to recognize between 0 and 9 for handwritten digits. It's pretty much solved at this point using convnets. Like people can get, like convnets can get like 99.98 accuracy or something like that. And the rest are just like digits that are like malformed or stuff anyway. So we've pretty much solved this problem as well as we can expect to. And CFAR is getting there too. So it's only 32 by 32 images. They're color, so a little bit more complicated, but the data set size is comparable. CFAR 10 has a comparable number of classes. CFAR 100 is a little bit harder because there's 100 classes. But these are sort of good ways to sort of prototype something that you're building. Don't start with ImageNet. Start sort of in this progression wherever you're comfortable, right? And then try to tweak things as you go along in order to make sure that things are actually working the way that you expect that you would expect them to. And there are more data sets that we haven't mentioned, but these are sort of the ones that a lot of people play around with. I only have 2 minutes left, so I think I'll just tell you about one more thing, and then you can read the rest of the slides if you're interested, but we didn't get to it, so we won't consider that officially part of the material, but I do want to tell you about maybe this next idea is kind of the most important one if I had to pick one, right? It's this idea that Sean O told you about last Friday about skip connections, right? So rather than just parameterizing the connection between ZL to AL, right, as just some nonlinearity like some ReLU, we're actually also going to include a direct connection from AL minus 1 to AL. This is the basic idea. There are variants of this idea, but basically what it allows us to do is right, we get better forward connections in terms of like our nonlinearity. You can't just like kill things for us. We have direct connection from AL minus 1 in case we want this layer to just learn nothing. That's possible, right? And we get better gradient flow backwards, such that our nonlinearity can't cause our gradients to be really misbehaved. This idea was popularized by a class of convolutional networks called residual networks or ResNets, and implemented the idea in 2 slightly different ways. I don't think we'll have time to get into this, but it's basically a variant of this skip connection idea that we talked about here. And really, this one's really important because before 2015, people really couldn't figure out how to build really large networks. Skip connections, if I had to think of one idea that allows us to build really large networks, it's this one. Pretty much every state-of-the-art neural network uses skip connections. I don't think that's necessarily true for any other one single idea that I could tell you about. And this really enabled massive performance increases even after the types of increases that we've seen before. So we see, this might be too small, the third bar is AlexNet, and we can see that this leads to a significant increase on ImageNet performance, right, compared to the first 2 bars. but it just keeps going down as the number of layers goes up, and the number of layers going up is facilitated by skip connections. Okay, we will stop there. You can read the rest of the slides if you're interested, but that's all we're going to talk about for ConvNets. Thank you.